going to be I'm going to be talking about a recent paper where we're combining it with genetic algorithms. So what I'll do in this talk, I'll mainly, well, half the talk will be discussing what genetic algorithms are. So I'm going to assume that you're more familiar with quantum annealing than genetic algorithms for obvious reasons. And so these papers, a lot of the work there is actually just pure genetic algorithm work, and then I'll show you how that can fit into quantum annealers. All right. Okay, so I hope you're enjoying my animation here. So the motivation, I should tell you, first of all, is that at the institute I'm in Durham, it's a particle physics institute. So my own motivation is really coming from a string theory point of view. And it's and what you find there is you have huge parameter spaces to search, like in a lot of problems. And so it's a sort of big data problem. And what we're interested in finding in all of these models is the standard model of particle physics. And in order to find it, what you're basically doing most of the time is just having to solve a set of equations which are integer. So it's a Diophantine equation. And you might want to, for example, get some particular property like 3 generations of matter and so on. And so it's a set of consistency conditions in a sense. So recently, in recent years, machine learning has been studied a lot in order to try and look at these things. And mainly what people do is they look at a particular technique, so just a single technique, genetic algorithms, for example. And what I'm going to be doing here is sort of trying to combine 2 techniques. So it's genetic algorithms and quantum annealing. So I'm not really going to be talking at all about particle physics, except to show you an example. But what I really want to emphasize in this talk is just that it's combining the 2 techniques in a certain way that can help sort of solve issues with both of them. Right, so this is an overview of the talk. As I said, I'm going to spend quite a while talking about genetic algorithms and how they work. And sort of once you've got the hang of that, it'll kind of look more obvious when I start to introduce the quantum annealing aspect to it, what the quantum annealing part is going to be doing for you with the genetic algorithm. I'll give you an example where I look at I'll just show you results essentially of what when we're trying to solve a problem, just so that you can see how a genetic algorithm kind of works to solve a problem, how it improves just over a flat scan. And you'll see that you can go and get orders of magnitude improvement on what you would be doing if you're just trying to do a straight search. And then the third part, I'll talk about how we combine them, and that the quantum annealing does improve the performance of a genetic algorithm roughly by a factor of 2. That's what we find. Right, so I'll start with genetic algorithm background. So just begin at the beginning. They're based on evolutionary dynamics. So what you do with a genetic algorithm is you have a population of basically attempts at the solution. So every individual in your population is an attempt to solve the problem that you're interested in. And what you do is you breed these individuals and you select them for breeding based on how close they are to solving the problem. And what you find is that the population will evolve until it sort of clusters around a solution to the problem. So that's the way they work. I mean, their advantage is that they're extremely efficient and they can look at sort of huge parameter spaces in a heuristic way. Disadvantage is that, of course, it's very hard to figure out the statistical information about the search space. Sort of by its nature, it's in search spaces that you can't just look at in order to get the statistics. So it's hard to get a statistical information. But so it's good if you just want to find a solution to a problem. So in that sense, it's kind of similar to the same sorts of things you're using quantum annealing for. Right, so I'm going to show you how it works just on a simple problem, which is this one. So suppose I have a function, this thing, with a cosine and sine there, and it's a function of 2 variables. I want to find the maximum, but I don't want to use calculus, or I don't know about calculus. And so this function is quite hard to use calculus to find the maximum of, you would probably, if you know about calculus, you would be using a sort of gradient descent probably to try and get close to the maximum. So that's what gradient descent is doing essentially. But it also, by the way, a genetic algorithm doesn't have to be for problems which are continuous. This is a continuous problem, but the technique works just as well if you just have a, sort of a block graph or something, a bar chart. It would work just as well to find the highest bar in the bar chart. So anyway, so let's find the maximum without using calculus. So this is how you can do it with a genetic algorithm. The first thing you do is you define an individual. So an individual is it's an attempt at the solution. And so what you can do is you can take your X and Y coordinates and you write them out, A point B, C, D, E, right? And Y is G dot H, I, J, K. And these are numbers 0 to 9. So in other words, I'm allowing X values to go from 0 to 10 and Y values to go from 0 to 10. And I want to find the largest value of the function in that domain. So you see, if I wanted to 250 decimal places, you get there's a huge search space in principle that we could be looking at. If we don't know this is a continuous function, we just think of it as a huge search space. Right, so this is our creature. What you do, a single creature, single attempt at solving the problem, you write out the coordinates. And the coordinates you think of as a genotype. So you think of that as its DNA. And so the data, the DNA, is it's called the genotype. The actual result, so the physical properties that are generated by the genotype, it's called the phenotype. And in this case, it's the function. So that's the thing we're interested in maximizing. So this defines a single creature. It's got its genotype, and the genotype gives us the phenotype. And what you do is you then, so that is somewhere living in the landscape here. And then what you do is you generate a population of these things, and it's typically about 100 or so of these individuals that are chosen at random. So you choose the genotype at random, and it corresponds to these individuals. So then what you do, the first step, is you work out the fitness of every creature. So you go around the population, and you look at its phenotype, and you work out how fit these are, how close to a solution are they. And in this particular example, you could take the function itself to be the fitness because you want to maximize the function. So you want to maximize the function, you choose the fitness to maximize the function. So we could just take the fitness to be the function itself. That's one way to do it. And then what you do is you select pairs for breeding such that the most fit individuals are selected more times for breeding than the unfit ones. So typically you would select the fittest one 2 or 3 times more than the unfit one for breeding. And you make breeding pairs of these creatures. So you'll select their genotype. You make pairs of genotypes, selecting them randomly, but biased by how fit they are. And so there's some probability of selection. So if n pop is, say, 100 or something, alpha is the number of times that the fittest one breeds more than the unfittest one. And so this is a way to write the probability of selection such that that's true. All right, so that's the starter. That's the first step. So the next step is then what you do is you take all the pairs that you've generated. So you've selected pairs for breeding. You take those pairs and you breed them. And by breeding, what you do is you take the genotype and you literally just cut it somewhere at some random point. It could be more than one point, but I'm just showing you the sort of simplest single point overlap. And you create 2 new creatures where you've swapped the tails of their genotypes. It gives you 2 new creatures, and that generates an entire new population. So what you then do is you throw away the old population and you take the new population. Then the third step is, which is an important step in this process, is a mutation. So a mutation step, what it does is you take your creature, your new population of creatures, and you go around and you change all of the, you change some of the alleles, a small percentage of the alleles, you'll just change them at random. And allele is the name for a single point on the genotype, right? So you just randomly select points, say 1 in 100 or so, and you'll just flip it to a different value. So that's the mutation stage. And as we'll see, it's an important step. It's very crucial. And then what you do is you just rinse and repeat. So you just go around doing that for several generations. And what happens is you'll find that the population converges around solutions. And so before I show you an example of what happens with this, I'll just give you a summary of the process as a flowchart, because this will come in later when I introduce quantum annealing. So this is what I'm showing you in this flowchart. I've got the genotypes on the left here. So this is where we start. We select breeding pairs from the genotypes based on the fitness. So these are ranked in terms of fitness. You select breeding pairs based on the ranking. And then you will breed them. So there's a crossover stage to generate a new population. So that's here. Then there's a mutation, which gives you a new set of genotypes. So this is the new population. And then what you do is that this is the important stage. You take this population, you work out for each one the phenotype. So that is there, in this case, it's the function value for those genotypes. So every member of the population comes with its phenotype. You then decide how fit you think it is. So this step I'm calling the environment. Is sort of by analogy with other learning techniques. So reinforcement learning, for example, it's a similar sort of flowchart, and there's an environment that you sort of confront your individuals with. From that you work out the fitness. So in this case, the environment is the function, and you want it to be as high as possible. So that gives you the fitness. You rank them, so 1 to n, and then you get the new set of genotypes. Right. Okay. So that's the summary of how it works. Are there any questions at this point? I'm going to show you it in action. No. Okay, so this is how it works. So this is on that function. There's a population of something like 50 or so. And then generation number 0, it's just completely random. And you'll see that after, say, 5 generations, the individuals start to cluster around the maxima. And you'll see that it does it. They start to focus on them also the local maxima. So it's not just the global one. They start to focus wherever there's a maximum. So it's there's a little bit of gradient descent going on, but they also get kind of sampling the whole parameter space as well. So generation number 10, like that, and generation number 20 looks like that. So you see what happens is very typical in this sort of what I'm showing you, is that you'll end up with the population clustered around a few possible solutions, and then what you then do is you'll kind of look around there to see, well, is the solution nearby? At that point, you can then do something which is a kind of exhaustive search in that region. But that's this is the advantage, really, is that you can kind of pick up areas where the solutions are going to be located. It works for very sort of choppy landscapes. So as I said, it doesn't have to be continuous, and it can have many maxima and minima. So this is a much more choppy landscape, and you see this is the actual value at this point, and you'll see that it works just as well. It takes a few more generations, so this is after 500 generations. Right, so why do they work? It's kind of a long story, and this technique was introduced by John Holland back in the 1960s, I think. I mean, it wasn't his idea, but he's the one that really sort of developed it. So it's usually attributed to Holland. And there's something called the schema theorem, which is that the idea of the schema theorem is that if I have something like a kind of some sort of function, which is there's a kind of maximum area, it can be the case that certain of the alleles in the genotype are much more important than other ones. So in this example I'm showing you, see the maximum is here, and you see that the X value is 6.1-ish, and the Y value is 6.2-ish. So if I just take, if this genotype is just the X coordinate and then followed by the Y coordinate, you see that these 4 alleles are much more important than the other ones. And so what happens initially is that these 4 alleles get sorted out before any of the other ones. As soon as you randomly hit on an individual which has got 6.1, 6.2, you know, so it's lining up along these 2 lines, that schema, it's called, which is basically the four important alleles, and then these stars are kind of wild cards you don't care about. That schema is propagated through the population exponentially fast. That's what Holland argues. So the growth of these important schema in the population is exponential, and it pushes it towards convergence. Mutation, on the other hand, so this business after we've done the breeding and we sort of mutate everything, that pushes the system away from convergence, but it stops you getting stuck in a local minimum. So the mutation will allow you to kind of explore outside a local minimum or maximum. So this is, I should say, the schema theorem, the Holland theorem, is quite controversial, and people more or less dismissed it in the 90s, and it was rehabilitated a little bit, somewhat, by, there's a series of papers by Polly. I would say that there's not many good general ideas as general as that. So there are quite a few sort of specific cases that people have looked at, but I think the schema theorem still has some value to it anyway to understand what's going on. There's other work about this, what's called the fitness distance correlation, which is essentially, if I'm somewhere in the search space, the Hamming space, and I get closer to a solution, that if there's a correlation to how close I am with the fitness, then that seems to be an important aspect. So it's a little bit of gradient descent aspect to it, having to be there, but it doesn't have to be that you can actually express things as a gradient. It can be, as I said, discrete problems also work. Right, so I should just probably hurry up a little bit because the time is rushing. But anyway, there are ways to optimize it. So one thing you can do is with the fitness, what often is better is to do something called a rank selection. So you simply take number 1, you select more than number 50. And your fitness is really defined by just the ranking, not any particular value, like, for example, the function value itself. The ranking is enough really to overcome. For example, the minima get very flat. You really just want the one which is slightly better. So ranking works quite well, we find. There's also something called elitist selection, which is basically that you'll always copy the fittest individual into the new population, so you don't lose the fittest individual. The fittest fitness never goes down. And then there's this other things you can do, which is to have more point crossover to avoid edge effects, and also that you can optimize the mutation rate. There's this kind of optimum mutation rate, which we'll see in a minute. And then there's this other thing called creep mutation, which is that a particular problem appears in this example. Suppose, for example, the solution was at 1.000, and we were at 0.9999. An individual was there. It's clearly very close. The phenotype is very close, but the genotype is about as opposite as it can be. And that's called a Hamming wall. So, just perturbing this 0.999 isn't going to get me very close to 1 if I'm just like randomly perturbing the 999s. So there's something called creep mutation, which is where you work with the phenotype. But generally, you're really just thinking about fiddling around with the genotype when you're doing this sort of operation. Right, so let me just show you an example. I mean, this is from string theory. You basically don't care what it is that I'm showing you, apart from the size of the search space, which for this example was 2 times 10 to the 15. We're looking for particular properties, and as I said, it doesn't have to be continuous, so these are discrete things. So we're looking for numbers of generations, for example, existence of a top Yukawa coupling. Doesn't matter if you don't know what that is, but anyway, there's a certain set of criteria which are all discrete. There's 5 of them, and in the search space, we know we can search this deterministically, so we know how rare these things are. So if I ask for all 5 of them, then it's 1 in 10 to the 10. So only 1 in 10 to the 10 of this in the search space has got all of these particular properties. All right, so let me show you what happens. If I ask for all of the properties, if I was just doing a flat scan, I would have to look at 10 to the 10 of these particular models. I'd have to make 10 to the 10 of them in order to find 1. And what we call that is the call count. So it's basically how many times do I have to do the thing to make the individual, to make the model, in order to find 1 which has got the properties I want. And what I'm showing you is the performance of the genetic algorithm as I vary the mutation probability per bit, per allele. And you see that what's happening as I get a high mutation rate, it becomes more or less random, and it tends up to 10 to the 10 at this end, which is what you would expect. If I'm just doing a random search, it would be 10 to the 10 calls, 10 to the 10 models I have to make in order to find 1 successful one. But the characteristic then of genetic algorithms is that if the mutation rate is optimized, I have to do far fewer. So I only have to do 10 to the 5 in order to find a successful model, so in order to satisfy all the criteria. Whereas if it's just a flat scanner, it would be 10 to the 10. So this is a sort of typical sort of performance of genetic algorithms. It's extremely efficient on problems where the problem is very rare to find a solution in the search space. So you see what I'm showing. So down here, see, if I only ask for 3 of them, A, B, C, there's a lot of them, a lot. So I think it was 1 in 10,000 satisfied the first 3 criteria. You see, it's not really doing much for you, the genetic algorithm. But once it's 1 in 10 to the 10, suddenly you start to get sort of orders of magnitude improvement. So that's the sort of general property of these things. Right, so now I'm going to get on to quantum annealing finally. So what we want to do is sort of improve this technique by introducing quantum annealing. So I'm going to give you a lightning introduction of quantum annealing. I'm assuming that you know what quantum annealing is, so judging by the name of this network. So this is a 1-slide introduction. What it does is it minimizes a Hamiltonian. There's it's a quadratic Hamiltonian in spins, and the spins are connected by couplings that you can choose, couplings between spins. You can choose the spins to couple up to, limitations on the connectivity of the thing. And also there are biasing couplings. So the first couplings are called J, and the second couplings are called H. And then there is the transverse field term, so this, which I'm calling delta, which is a sigma in the X direction, so a transverse spin. And by turning on this thing, you introduce hopping. And the idea is what you want to do is you want to dial down the transverse field thing as time goes on, and you want to dial up the couplings. And the idea is that you end up in the minimum of the sigma Z Hamiltonian, and that's where you will put your problem. So you encode your problem in the sigma Z Hamiltonian. So that's the sort of lightning overview. I'm going to use, was it Coleman's statement? Are there any questions? If there are any questions on this slide, please leave the auditorium. Okay, so you should, I'm assuming that you know these things. Right, okay, so the problem with this technique, and we've come across this ourselves, is that if you have even a mildly tricky problem to encode, very quickly you will fill the whole annealer Right, so what I'm showing you here is that we've encoded this particular problem. We want to find the solution to the equation x1 squared plus x2 squared equals 149. And so to do it, you can encode it as the square in the Hamiltonian. And you can represent these numbers, these integers, in a binary fashion in terms of the sigmas. And so this is what I'm showing you is what the Ising model looks like in order to encode this problem and solve it. And this problem is quite simple. It's just solving a quadratic, and it's a Diophantine problem. So I'm just looking for integers, which I encode in a binary. But you see that even for this problem, encoding that thing on the annealer, I'm using 22 qubits. So the qubits are represented by the blobs here. The colors are representing the H coupling. So red is negative and blue is positive. And then the couplings are the straight lines. So those are the quadratic couplings. And the strength of the line is the strength of the coupling. So you see that the weaker couplings are quite are faded, and then the stronger couplings are stronger lines. But you see, it's extremely complicated, even just to solve this thing. So to encode something like, solving for the standard models and putting a string theory on an annealer, you basically just fill the whole annealer within, before you've even got close to putting the problem on there. So, I mean, part of the problem is that this is a quartic equation. So when I'm encoding these things, I need a lot of auxiliary qubits to make it a quadratic spin Hamiltonian, to encode it in a quadratic spin Hamiltonian. That's why I need 22 of them for this particular problem. Right, so I'd say this is a generic issue with quantum annealers, how hard it is to encode problems. Right, so instead what we want to do is kind of combine the best of both worlds, and we're going to take our flowchart for the genetic algorithm and we're going to sort of put it into quantum annealing language. So this is what we can do for our individual, our genotype. We can embed the genotype into the H couplings. So the H couplings, which are continuous, those couplings can hold our genotypes of the individuals. So that's what we call an individual. And when you're doing an anneal, what happens is that these things give rise to binary spin values. So it's 1 and -1, but you can cubo it to ones and zeros. So it gives you essentially a genotype answer. So it gives you a discrete answer. So we call that thing the quantum genotype. So this is our definition of a creature. It's got a continuous set of biasing couplings, of H couplings, which give rise to the discrete genotype. So that's the thing that you're going to build your phenotype out of. So that's the kind of what the creature gives rise to is the phenotype. And from that, you work out the fitness. So that's how we're going to encode our population. And so if you go back to the flowchart, so these are all of the H couplings of the genotypes. See, the flowchart looks the same. So we can still rank those things, and we can still do selection. We can do crossover to get new genotypes. And these are all the H couplings, remember? The mutation stage is the thing we replace with the annealing. So at this point, in order to get the discrete output, so the binary genotypes, we do an annealing phase, and that is the point where the mutation comes in as well, right? At this point, when we go down here, everything is classical at this point. So this is the same as it would be in a normal genetic algorithm. We work out from the discrete output, we work out the phenotypes. That's the phenotypes. We then confront it with the environment. We work out the fitness. We can then rank them. And then, we reorder them by ranking. And then we do our selection and so on. So all of this stage here, all the way around this loop, is classical. This is the point where the annealing comes in. So you can think of it as a kind of, as a directed mutation. So it's directed by the biasing. And it's directed towards the solution that you want. In addition, we of course have our J couplings, and what that means is that if we have in the population an individual that's very fit, and we want all of the others to know about it, we can use the J couplings to do that. So, and this is what you can't do in a normal genetic algorithm, is that we can have a coupling between say the fittest individual and the weaker individuals. And what that allows you to do is it sort of replaces the need to have many fit individuals in order to have them influence the rest of the population. It allows us to reduce the population number because we can couple the fittest individual to the other ones and make them bias the other ones during the annealing stage. So that's so these are some examples of how we do that. So what you're seeing here is basically you're looking down a column. So this is the fittest individual, and this is the weakest individual. And the J couplings are coupling the fitter ones to the weaker ones. So that's what these little islands are. It's coupling, say that this is the fittest one, coupling to the next fittest one, and the third fittest and the fourth fittest, and so on. Right. Anyway, so this is what happens. What we can do is you can take a simple problem, and the problem that I'm taking here is to find solutions to this equation. It doesn't really matter what the equation is, but say you have this problem. I want to find an equation where I have the sum of 8 cubes in 2 different ways. So it's sum of 8 cubes, different cubes, right? So this is x1 cubed plus x2 cubed plus blah blah x8 cubed is equal to y1 cubed plus y8 cubed up to y8 cubed, where the x1s and the y1s are not the same. So this is the problem. That they're called taxi cab numbers when you get that, and this is just looking for solutions to that equation. And you see that if I compare the genetic algorithm to the genetic quantum annealing, what you find is that the genetic quantum annealing is improving its fitness much more rapidly than the genetic algorithm, than a classical genetic algorithm. And it does it in this also characteristic way that it has a rapid improvement, and then you have some kind of stasis, and then there's another rapid jump. And this is not kind of a numerical artifact, this is reproducible. It'll do it. It does it every time we do the experiment. It has the same feature. We can't quite figure out why this occurs, actually, that you get these rapid jumps. Anyway, so that's how it works. And you see that if you look at the fitness, how it improves, you get something like a factor of 2 in the performance of it. So it's kind of roughly that sort of improvement. And so where it is useful is if it's really expensive to do calls, if I really like a factor of 2, if it means a lot to me in terms of computing time, then it's useful to use this sort of technique. So let me finish there. Sorry for running over a little bit. So I've shown you this technique of how to combine genetic algorithms and quantum annealing. As I said, it does appear to reduce the number of times you have to call the problem. So it's useful for problems when the actual figuring out how good the attempt at a solution is very expensive in terms of computer time. The useful thing about it is it allows the environment to be kept as a classical computing step. So it sort of keeps that benefit of genetic algorithms that you can kind of bolt on your classical computing, whatever the problem is, you can sort of bolt it onto this genetic quantum annealing thing in order to kind of have a population which improves. That's the same sort of thing you do with genetic algorithms. You don't have to encode the entire problem on the quantum annealer in order to get this sort of improvement. You keep the problem, the computing for the problem itself is just kept as it was. As I said, it's useful when the problem is expensive to compute. So, you look at an order of 2 sort of improvement, but we still have to kind of study how much you can optimize this sort of thing. Those sorts of studies are kind of hard to do because, access time to the quantum annealer is not that easy to get. And it's also, it takes time to do the study as well. So, you have to use a lot of time to do the study. But still, in the end, we'd like to do something similar to what we do in the classical genetic algorithm to kind of optimize all of the parameters and get a kind of optimal solution. Right, okay, I'll leave it there. Thanks.
Great, thank you very much, Stephen. Lots of interesting things. I shall give you a round of applause on behalf of all the audience members. Thank you. And open it up for questions. So are there any questions for Stephen? Maybe I'll start with a question then. So if I've understood you correctly, when you're doing these quantum annealing modifications, there are essentially 2 differences. One is that your mutation comes now from the quantum annealing process.
Yeah, that's right.
The other difference is that you have these couplers that allow your fit individuals to breed more strongly or something.
That's right. Yeah.
So I'm guessing that first thing you could also implement classically in some sort of modification of your genetic algorithm, completely classically. And I'm wondering whether
you mean to have a continuous, to define a genotype in a continuous way and then have an individual defined that way. Oh, it's the thing about, sorry, what was it? What were the 2 things?
It's the couplings. It's the couplings between.
The couplings, right. The couplings you could do, you could do classically, but I mean, I think part of the problem with the coupling, or the reason why it's not useful in the classical case, is the classical case you're usually encoding it in a binary way. So the genotype are just 0s and 1s classically. I think if you, what you need to do is you have to encode into the alleles, the 0s and 1s, a kind of also some sort of memory of how fit the individual is, how fit its parents are. That's really the thing which is giving you and that's in the biasing couplings. So you really need, it's useful when you have a continuous coupling, which is defining the genotype. So what the annealer does, which there isn't really an equivalent in classical computing, is I mean, you could do it just randomly, but it means that you get from a continuous genotype to a discrete output, to the discrete individual. And so, all of the coupling and the biasing and so on is done in terms of the couplings, which are continuous, but then the output is discrete. You sort of work with the binary output like you would normally do. So that's where it makes a bit of a difference. So if I was to do it classically, it's not obvious how I would do it classically. I guess you could define some sort of equivalent to an annealing process where I kind of select a 0 or 1 based on the value of
in my mind, I'm trying to separate these 2 effects. One is the role of the coupling that you've added, and one is the role of the annealer as randomizer.
I mean, they're slightly entangled a little bit. I mean, not technically entangled, but they're sort of they're mixed up a little bit. So they're all there on the annealer essentially.
Let's move on perhaps to some other questions. So Victor Durham Touchette.
Yes, hi. Thank you. I had a question. If you go back to your slide, I think you can still show your slide, I think, right? With your diagram of the full genetic quantum annealer.
Okay. Let me just go.
So I think I understood well where the H comes in. Those are the things that really update from one step to the other. But I think we're going to go back to the issue of the J's. I don't understand whether the J's in the actual, let's say if I think of D-Wave's quantum annealer, how the J's are updated themselves, or whether they actually are updated, or you just change
right. So that's a good question actually. The J's at the moment we don't update them, we just leave them as couplings which are fixed. And so what I'm showing you is sort of one a kind of combination. So it's the similar sort of thing, that the strong lines are the stronger couplings, and also you see the wiggly lines are negative couplings.
Yeah.
And we just keep them like that. We don't update those at all.
So you start from a specific graph and then proceed with the algorithm on that specific graph that you've kind of created.
Yeah, that's right.
Okay.
Yeah, because I think updating them, it would be difficult, because you'd have to you'd have to restart everything. And what you want to do is you want to do a lot of reads, basically, without having to start everything from scratch.
And just a second, very quick one is that, do you have to like do a precision kind of threshold for your H's? Because D-Wave itself has some precision that you can't tune the H by like 0.005 or 0.005 or something. Does that influence the power of the algorithm? Because you can't update the LEs all the way there.
Yeah, we're not at that level of accuracy that we would notice that. I mean, what tends to happen, it's quite a, I don't know what you call it, it's sort of unstable, I suppose. That's why we need to work a lot more on how to optimize this thing, because you know we have the negative couplings in the J as well as the positive ones. The reason we have that is because we just found that if they're all positive, what happens is it will immediately crunch to a local solution, and it'll just get stuck there. So that's the equivalent, I think, of just basically not having enough mutation in the classical. It would just like sit in a local minimum. And so we kind of need to have the negative J's in order to sort of keep the population moving a little bit. So it's quite sensitive to how you vary parameters. And at the moment, we don't, well, I guess you have experience of running these things, but, you know, to actually be able to vary all of the J's and all of the H's, and to find which is the, you know, and the parameters of the anneal schedule as well, you know, the time, and ideally you would like to optimize all of those things, but
that's challenging.
It would take a long time to figure out how to do it. So I guess you could kind of do one at a time, you know, you would just vary one thing and try and but that's why it's hard to figure out how to optimize these things. Hopefully there is somewhere out there a choice of parameters which will be, you know, a great optimization, which will give you orders of magnitude improvement. That's what we want.
Yeah. Thank you.
Yeah.
Okay, Sugato has a question.
Hi.
Hi.
Very, very interesting talk.
Thank you.
So again, I don't know whether I understood everything correctly, but let me. So have you tried to do some dephasing of and while you're doing the annealing, then maybe you see that does your advantage go down when it is not genuine quantum process, like when it becomes, you know.
I'm just trying to remember what we looked at. I think we don't, so that we don't know really. So we didn't look at that. That would be a useful thing to look at. I mean, we didn't at the moment. But...
And another quick question, so just trying to understand so it's similar to Paul's question, what exactly your the quantum annealer is doing. So it's some kind of, am I right to understand, some kind of randomization, but under the constraint of the energy keeping?
That's right. So you should sort of think of it as a directed mutation, and so people this is what other people, I mean, so other people have also looked at similar sorts of things, but where there was a kind of directed mutation. So there's a review of Nick Chancellor's where he kind of reviews a lot of these things. So it's sort of become known as directed mutation. I think what no one has done really is to find a configuration where I can literally take a classical piece of computing, which I've got already, and just bolt this thing on, which is the advantage of genetic algorithms. And so that's the advantage of our thing. What the quantum annealer is doing is then kind of is, you should think of directed mutation. That normally mutation is just a kind of random flipping of genes. In this case, it's flipping genes towards the individuals which are fitter, you know, with some biasing. So it sort of generally should allow you to have less, smaller populations. That's where the advantage should be.
Okay, no, that's very interesting. So it would be very difficult to do this in a gate-based model or anything else because you don't have this constraint, right?
Yeah, so a gate-based model, I mean, of course, you could do anything in a gate-based model, but yeah, I'm not sure how you could do it. And the other thing, of course, is you need a lot of qubits to do it. But yeah, so you need the population. As it can be smaller, but you still typically would need, say, 50 or so. And if you're in these problems that we were encoding, so say if you're doing the taxi cab number, so you've got to encode cubics to the 8. So, you know, your genotype is going to be, say, 50 long and then 50 individuals. So, you know, you're sort of filling the annealer.
Okay, thank you.
Yeah.
Okay, Viv Kodo has a question.
Hi, Steve.
Hi.
Nice stuff.
Thank you.
Just to make sure I'm understanding, so you're running the, I mean, you've got the classical bit with all the genomes. So, and the fitness function is applied to the classic, is all done classically. Yeah.
Yeah.
And then what you put on the quantum annealer is just the population, and it's just the rankings that are defining the problem, if you like.
That's right. Yeah. So, and the ranking is all done classically as well.
Yeah. No. So you have the ranking, and so it's doing the directed mutation process is just on the genome, and it's just that you have the rank that tells you which way to go. You're not explicitly using the fitness function. That's what I'm just checking.
That's right. Yeah. I mean, so there is so one thing I should say is because when you're writing the new population, the biasing coupling, so the H's, are related to the fitness, so that the fitter individuals can also have higher biasing. So they tend to bias their children more because their couplings are stronger, you know, their H couplings are stronger.
Yeah, no. But you don't explicitly have the function in there anyway.
That's right.
What
Yeah, exactly.
It's just that the individuals have just the ranking that was done. So it's an implicit fitness in the mutation.
That's right. Yeah, exactly. Yeah.
Right. Because I was just reflecting that the fitness function itself is actually quite simple, right? So it's the most compact information you have about the problem is the function you need to evaluate.
Well, it depends.
It's the hardest. I mean, the values it takes, of course, and finding the, you know, so the reverse, finding the X's and Y's or whatever, the values that satisfy it is one thing. But the function itself is...
Oh, the function itself is very simple, yeah.
It's very simple.
Yeah.
So I was just reflecting on the fact that you're not putting, if you like, this compact information is not what you're using the annealer for. You've expanded it into this population, and then you're messing with the population based on that sort of simplified, linearized, if you like fitness that you've got.
Right.
You've got a ranking for it.
Yeah, that's right. So yeah, the main thing is that all of the complicated stuff you want to just do, that has to be done classically, and the annealer is really just working on the simple, on the fitness functions and so on, and ranking. Yeah. No, I
was just wanting to, because otherwise, if you were just randomizing, it's not clear whether the problem got put on the annealer. That's why.
Oh, right. No, yeah. So the point, the problem itself should not go on the annealer. I mean, those are other interesting things to put the problem itself on the annealer, but we're kind of interested in problems which are quite so hard that they can't really fit on the annealer. So, for example, you know, relic abundance of dark matter or something. Yeah, I mean, there are so many things that you're calculating. You would just never be able to put that stuff on an annealer.
Right. Okay.
No, even if you had millions of qubits, it would be impossible.
Yeah, no, the confusion here is your example was too simple.
Yeah, it was exactly. The example is simple because we don't want to. Yeah,
Because you've only got the x and the y variables there. So the jump between that and the number of variables you've got, and that was throwing me off, right?
Yeah. Okay.
Yeah. So okay, no, I get it now. What you've got is like this much larger variable space.
Yeah, exactly. Yeah, that's
like
right.
50 rather than 2, and that's why you have to linearize the problem into the rankings. Okay, good. I'm clear now.
Good. Thank you very much. Thank you.
Thank you.
Thank you, Stephen. Thank you, members of the audience. I think we should probably conclude there. So another virtual applause on behalf of everyone for Stephen. And a reminder that there is the International Travel Grant Scheme for members of the INQA network, which people can apply to with a deadline of early February. I forget the precise date. We'll be sending reminders about that on the network mailing list soon. And the next seminar is in a week's time, as always. Thank you for attending, and I'll see you all soon. Thank you, Stephen.
Yeah.
Thank you. Bye.